Okay. Lots of things to go over today, things I think you will want to hear because I'm going to go through the data analysis for experiment 14, which you need to know about for your experiment 14 conclusion, and we'll go through the practice exam. So let's go through a couple announcements real quick so then we can get started on the data analysis. Registration for Chem 256 for the spring. If you have any changes that need to be made or you need to see me for paperwork, see me ASAP. I need this finalized because numbers are so tight, I can't do anything for the next person that comes to see me until the previous person takes care of their paperwork. So make sure if you have paperwork out there from me, get it to the registrar's office by tomorrow morning. If you need to see me for paperwork, see me right after lab lecture today. We need to get that finalized. Cure survey. So you guys took a survey at the very beginning of the semester that Dr. Gilmore sent you Moodle messages about, and you took that survey. We need to take the survey again now that you've had one semester of lab. So you should look for an email probably from Dr. Gilmore or Moodle announcement from Dr. Gilmore to complete the survey before the end of the semester. Okay, and the instructions and a link for that will be given to you. And then see your lab prof for your experiment 14 due date. It's technically due sometime this week. Each lab prof has their own date and time for that, so make sure that you are clear on your own report due date. Okay. All right, so I am going to, first we're going to go through experiment 14 and data analysis for it. And then we will give some of these lights here for you. Then we will go through the practice exam. So I have data up here that's from an example of experiment A reaction conditions. So remember 0 degrees, 1 bromopropane were used for this experiment. And so we're going to use this data to go through the data analysis example for one set of reaction conditions. So there's 4 tables that you have to put together for experiment 14, and you want to put those tables together before you come to lab this week. So Tuesday morning, people, remember, put those together by tomorrow morning, Tuesday afternoon by tomorrow afternoon, so on and so forth. But you want the tables before you come to lab because any data discussion doesn't really make any sense unless you have those tables, okay? So the first table that you're going to put together is for your own data. No matter what your reaction conditions, that table is just for your particular data. Okay, so make sure you're using your data set for this. And you're going to go through and use the standard retention times that were given to you by your lab prof and make assignments on the peaks that are in your data. All right? So we know, based on the retention times, we can identify toluene, we can identify metapropyl and ortho-isopropyl toluene, metapropyl and ortho-propyl toluene. Now these standard retention times are probably not exactly what you were given to you by your lab prof. They're what fit this data, okay? So don't record these exactly. Take what your lab prof gave you. That's what's going to fit your data. Something that you weren't given is the dialkylated toluenes are usually between about 13 to 16 minutes. So if you have peaks in the 13 to 16 minute range on your data, that's probably dialkylated toluene. And then the trialkylated toluenes are probably 20 to 23, 22, 23 minutes or so, okay? So you want to list the compounds, list the standard retention times, and then give the experimental retention times, okay? Now in this case, I did not give all of, because I ran out of room, of chalkboard here. So my 13 to 16 minute peaks here, I didn't list all of those retention times here. Your table you should, okay? So you want to list 13.404, 14.334, 14.798. Identify that as dialkylated toluene. Okay, and then same with the trialkylated toluenes. I didn't list all of the peaks between 20 and in this case, almost 22 minutes, because I ran out of room, but you need to do so for your table. So your table 1 is going to, in some cases, be a pretty lengthy table, all right? And then on the bottom here, I've got an unknown, possibly 4 or 3 other propyl groups, or sorry, 4 other propyl groups added on to that toluene, possibly 26, but we don't know what that is, so I've listed that as just unknown here on the bottom of my table, okay? But that first table, you want to be identifying the peaks that are in your own chromatogram for your own experiment, for experiment 14, and based on this, what you can't identify, then you will list as unknowns. But for the most part, you should be able to identify pretty much everything in their chromatogram, okay? All right, table 2 then, we're going to start now looking at everybody's data for your group, not just your own data, okay? Now for the next 3 tables, I've only filled out experiment A data because that's what we're looking at. But you will fill out the entire table. You will have data for experiment A, B, C, and D, okay? So table number 2, we're going to look at toluene, and then the relative percentage of toluene, relative percentage of isopropyl toluenes, relative percentage of propyl toluenes, and relative percentage of dialkyl toluenes, okay? Now to do this, we have to do a little bit of math, okay? And so we are just looking at basically all of the peaks here, and then down into the dialkylated toluenes, okay? So you're not really looking at the trialkylated toluenes, so just these peaks here. So what we have to do is use that peak area, so that column that you're given as peak area on your chromatogram, we have to come up with a new area. So this number on the bottom is the sum of all of these areas all together for the entire chromatogram. You now have to add together all of the areas that pertain to the toluene, the isopropyl toluenes, the propyl toluenes, and the dialkylated toluenes, okay? And so you will add all these numbers up together and come up with a new total, all right? Then once you add that new total, then you'll take, for example, the toluene. Take this peak area divided by that new total. That's how I got the percentage that's on the board. Then you'll take your isopropyl toluenes, which are these 3 right here, add those together, divided by the new total. That's how you get the isopropyl toluenes. Then you'll go through and do the same for the propyl toluenes, which are right here, and you'll do the same for the dialkylated toluenes right here, okay? Any questions on that? Yeah?
The peak area?
Peak area. So you have to use the peak area. Not peak height and not any percentage, it has to be peak area. Yeah?
So we would ignore any unknowns in the mix.
Yeah, if you have any unknowns in the middle of all that, don't account for those in your areas. Okay? So you do have to recalculate areas, though, to do that. Right? And if you wanted to, you could also include trialkylated toluenes in this mix, too, if you wanted to include it in the table. What your lab manual tells you is just toluene, isopropyl toluenes, propyl toluenes, and dialkylated toluenes. Actually, I think, let me double check. We might have amended that, so let me peek really quick. Seems like a familiar amendment here. Yes, so include trialkylated toluenes in that table too. I didn't put it up here, but do include trialkylated toluenes.
Should we include that in our percentage as well?
In which percentage?
Like counting it in there, or still don't count it?
Yeah, so what you'll do is, sorry, instead of this line down here, we'll go all the way down for the trialkylated. So do include those. Follow your lab manual. I had forgotten about the change we had made. Okay, so trialkylated toluenes will be in table number 2 as well. All right? Everybody clear on table number 2? Now that I've told you one thing and changed it, and now,
Yeah.
okay, that should be really clear, right? Okay. Okay. Now, one thing you want to do with all this is check and make sure in the end, when you get all these percentages, they should add up to 100. Okay? So each column here that you are doing this for each set of experimental conditions, it should add up to 100%. Does that make sense? Yes?
You want us to do each experiment on our own before we meet with our group?
Yes. Yes. You should in some form have that data. Or you should in some form be submitting that data. But you want to have all this data before you come to class. Okay? All right. Now for table number 3, so kind of will look a little bit like table number 2. Give compounds percent A, percent B, percent C, percent D. Table number 3, we're going to look at just the isopropyl toluenes. Okay? And so for just the isopropyl toluenes, we have to look at just the area of the isopropyl toluenes. So those guys are right here. So we're going to add up these 3 areas. That's your total, and then take each one divided by that total and get the percentage. And again, you want it to add up all to 100%. Okay? Questions with this one? Okay, and then the 4th table, you're going to look at the propyl toluenes. And so you're going to add up those areas, these 3 right here, get your total, and then take each one and divide it by that new area to get the percentage for the propyl toluenes. And again, you want that total to add up to 100%. So for tables 2, 3, and 4, each of your columns, remember, you want to, once you get the percentages, add them together, double check that they all add up to 100. Otherwise, the math is funny. Okay? And then when you guys get together in your groups this week, everybody's tables for 2, 3, and 4 should agree in a group. Okay? So you use the same data to get there. Everybody's table 1 will differ because that's your own data. But 2, 3, and 4, when you're looking at it in a group, all that data should agree. So that's the first thing you should probably check when you get together with your group. Does that data all agree or not? All right? Now, once you have all this data, then we have a bunch of questions for you on page 1410 that you will need to answer in the conclusion of your report about this data. Okay? Now, when you answer those questions, you don't want to just give, okay, answer number 1, this, answer number 2, this. You want to incorporate it in paragraphs in the conclusion. All right? So make sure that you incorporate it in what you are addressing in your conclusion and not just give written out answers. The other thing you need to use your GC data for, and so don't forget that you need to use your own GC data for this. Remember that you took the mass of your final reaction mixture after you worked it up at the end of experiment 14. You now need to assess how much of that is product. So use your GC data to figure out how much of that is product. Okay? And there's multiple ways you can look at it. You can look at it as monoalkylated product, and then you could do the calculation to include dialkylated product, and you could include trialkylated product. What you were looking for was monoalkylated product. But you probably got some di and trialkylated product in there too, especially for the warm conditions. Okay? Now, another thing, a couple things to review is when we talked about this experiment, we were looking at substitution on the aromatic ring, and we talked about kinetic products for that substitution. So what were the kinetic products? Ortho and para, right? Ortho and para substitution were our kinetic products. What was your thermodynamic product? What formed the most at high temperatures? Para? Who had a high temperature reaction? What did you get the most of? Meta. So you should see meta as your thermodynamic product, okay? So some of the data may not agree with that, but that's what should happen with the experiment is you should see meta product being your thermodynamic product. So that's something you're going to have to think about. You've got ortho and para, kinetic products. Your meta product is your thermodynamic product. The other thing you need to think about is the rearrangement of the carbocation when you use 1-bromopropane. And that's part of what you're going to get from these tables. So if you didn't get rearrangement, what did we call that? Was that kinetic or thermodynamic? Kinetic. If you did get rearrangement, that was thermodynamic. Okay? So you've got to keep straight substitution, final product, substitution on the aromatic ring versus what happened with the carbocation if there was a carbocation that could rearrange. So if it's easier to think of the carbocation in terms of did it rearrange or not, think of it that way, and then look at your substitution on your aromatic ring versus to see if you had kinetic or thermodynamic product distribution. Okay? Does that kind of help with the two things you're looking at? Okay, so keep those ideas in mind. And like with experiment 8 and 11 and 7 and so forth, your data, your conclusion is going to go in your notebook. Make sure all your GC data gets into your notebook as well, because we need to be able to see your GC data in order to then look at your analysis. All right? Questions on the analysis at all? Okay, so let's talk about, I'm going to turn this guy off for now. Let's talk about the final exam. So remember, Thursday, December 12th, 3 to 5, right in here, we will be meeting for the final exam. Okay? Make sure, and I'm going to go through these items here, but make sure you are here on time. Do not come in the room until we have you come in the room. So if you get here early and get here before me, wait out in the hall. Don't come in the room, because if you're in the room, I'm going to make you leave because I got to get everything set up for the exam, and then I'll invite you back in. All right? But remember, be here on time. I will start the exam right at 3 o'clock. So be here December 12th, 3 o'clock. Okay? Things to bring with you. Your calculator. Make sure your memories are erased. You can't use a cell phone for this exam, and you will need a calculator. So make sure you bring it with you. Ruler. Remember, now with TLC, we've had to use rulers to make measurements. Bring one with you. Pencil or pencils with an eraser. I highly recommend doing the exam in pencil. Don't do it in pen. It makes it a lot more complicated to figure out what your answer is if you have to scratch it out. Okay, so pencils, not pen. Make sure you bring erasers. If you typically take your lecture exams in the Academic Support Center, and will be taking this exam in the Academic Support Center, you need to see me. I am the person who has to sign the paperwork for this exam. Not your lab prof, not your lecture prof, but you need to see me. Now, if your lab prof is me and you need to see me, then that's fine. But you're not seeing, if you don't have me for lab, don't see your lab prof, see me to sign that paperwork. And we need to take care of that today or tomorrow. Okay, so you need to ASAP get that paperwork taken care of. Since this exam is at the end of the day, I will probably need to be getting exams over to the Academic Support Center earlier than 3 o'clock, and I need to know that. So make sure, get that paperwork to me, get it signed. So I am certain of what I need to do with those exams, all right? But make sure that you basically have these 3 items for the exam, all right? And don't forget them, okay? Before I go over the exam, one other announcement I wanted to make was about evaluations during the lab this week. One of the things that we're going to have you do is complete evaluations. And one of the evaluations that all of you will have to complete are the SALT evaluations that are online. If you don't want to have to do it in lab and wait to be done being checked out in lab, make sure that you complete that evaluation before you come to lab this week. While you're doing your lab evaluation, do your lecture evaluation too, okay? But things will go more quickly in lab if you have the SALT evaluation completed before you leave. Otherwise, you will need to wait to do that. So before you leave or before you come to lab, have your lab SALT evaluation and your organic lecture SALT evaluation completed, all right? In lab this week, we'll go through the data discussion. So go through now looking at and analyzing your tables and answering the questions at the end of experiment 14. Then some portion of the lab will be spent on what other evaluations you need to do, or if you didn't complete the SALT evaluation. You'll check out of your drawer, so make sure that you bring your lab key with you, otherwise you'll be charged $10 to replace it. And then you'll check out of your drawer, and then you'll have some cleanup task in the lab as well to help get everything cleaned up for next semester. Okay, so kind of four things will be happening in the lab, probably a couple of hour-ish or so in lab this week, all right? Morning labs will be meeting at 8 o'clock this week instead of 7:30, give you a half-hour reprieve. Afternoon labs, you'll still be meeting at 1 because you want to get out later. You don't want to stay late, okay? So you'll be, afternoon labs meet at 1, morning labs meet at 8 o'clock. All right, questions? Okay, you guys ready to go through the key very quickly? We've got 33 questions, so we kind of have to go speedy here. Okay, I show you this first page. It looks like just the title page to the exam, but notice there is a point available here on the exam. Don't forget to mark it. That is the freest point of the exam, so don't forget it. Okay. Number 1, which of the following are considered to be criteria for selecting a good recrystallization solvent? The solvent must have a boiling point below 50. No. The solvent must not react with the solid to be recrystallized. Yes. So number 2, the solvent must have a boiling point above 110. Nah. The solvent or solvent vapors must not present a significant health hazard. Yes. The solvent should be quite soluble in the solvent at or near the boiling point of the solvent, but should be much less soluble in the solvent at room temperature or below. Yes. So 1, 3, and 5, right? Sorry, 2, 4, and 5. See, good thing you guys are paying attention. Okay, so the answer is G. Which of the following compounds contain a carboxylic acid? Number 1, right? Because there we've got ether, ester. Here we've got an aldehyde ether, another ether, and then ketone there. So number 1. Whoops. Arrange the following compounds from nonpolar to very polar. So what would be our least polar compound? 3. Then what would be next? 1. Then what would be next? 5, right? With the OH group there versus the acid. Then what? Then 4, and then what? 2, because it has the charge. So that should be letter E. A cadet at the Air Force Academy at Colorado Springs was distilling toluene from his experiment. The atmospheric pressure that day was very low. His observed boiling point would be 110 because only melting points could be affected by atmospheric pressure. No. Lower than 110 because the atmospheric pressure was lower than standard. Yes. So the answer is B. Okay, which of the following structures represents the lowest energy conformation of trans 1,3-dimethyl cyclohexane? A, we don't have 1,3, right? B, is that right? Yes, right? We've got 1,3, and it is trans because if it was cis, it'd be axial-axial. But with 1,3-dimethyl cyclohexane or 1,3-cyclohexane and trans, it's going to be axial and equatorial. So the answer is B. Okay, the following table lists the reagents for trimericin's hydrolysis. What you have to do is figure out what the limiting reagent for the hydrolysis is. It's kind of hard for me to show you all this math and cover it up at the same time here. So I've gone through, calculated for trimericin. We were given 7.23 grams. Its molecular weight is 723.2. So there would be 0.01 mole of trimericin present. The ethanol, we've got 50 milliliters. We use its density, 0.79 grams per milliliter, and then we multiply it by the inverse of its molecular weight. We get 0.859 mole, so that corresponds to a solvent. A lot of it is present. So that's not going to be the limiting reagent. Sodium hydroxide, we've got 14 milliliters of it. We've got to convert milliliters to liters because then we have molarity in there as well. Then we use the molarity. And then we also need to consider, remember with trimeristin, for every mole of trimeristin, you need 3 moles of sodium hydroxide, okay? So you need to consider the mole ratio in there. So then you get 0.00933 moles of NaOH. That ends up being the limiting reagent, okay? When you go through the math for the HCl, same thing as the NaOH, we use its volume, convert it to liters, multiply by the molarity, use the mole ratio of 1 mole of trimeristin to 3 moles of HCl. We come out with 0.0117 moles of HCl, so that's not the limiting reagent. So the answer is C. Okay, does everybody see that? So if you end up with a calculation for experiment 3, or in any of these calculations, don't forget mole ratios. Okay. Physical models can be utilized to approximate all of the following except, so 3D configuration, yes. Possible bond rotations, yes. Ring strain, yes. Electrostatic potential, no. So the answer is D. The skeletal structure of trimeristin is. So, is it 1? No, what do we have and what are we missing? We're missing the oxygen in here for the ester, right? And then we've got this alcohol off the end. Is it number 2? Is it number 2? No, because it's not. They're not all of the esters are connected to 1 carbon, right? Is it number 3? Yes, the answer is 3. It wasn't 4 because again connectivity here, and it's not 5 because we've got our esters going the wrong direction. Okay, so the answer is C. A lacrimator is a chemical that causes a severe rash when it comes in contact with your skin. No. A chemical that causes you to speak with a high-pitched voice when inhaled. No. A chemical that causes you to laugh hysterically when inhaled. No. An irritant that causes your eyes to tear and water. Yes. So answer is D. Which compound is most polar? Something that dissolves in ether but not water, Water but not ether, both ether and water. B, right? Something that is most polar will not dissolve in ether, but will dissolve in water. Okay, so we have this IR spectrum for an unknown for experiment 6. Which of the following characterization tests would give a positive result? So what, from this spectrum, what do you see in here that you would possibly be testing for? What is this guy? It's at the 1700-ish, so that's carbonyl, right? So what test would you do for a carbonyl? 2,4-DNP test, so that's answer D. We don't really see any signs of, definitely nothing for the CAN test, which is OH. Silver nitrate test, you're not really going to see through the IR. Potassium permanganate, we didn't see any signs of the alkenes here, so we wouldn't have done that test. During a fractional distillation of a two-component mixture similar to that performed during experiment 4, a student simultaneously monitors the temperature of the boiling mixture and the distilling vapor. What is the relationship between the two temperatures? The temperature readings are the same throughout the distillation. No. The vapor temperature is often higher than that of the boiling temperature. No. The vapor temperature is most often lower than that of the boiling mixture. Yes. And it can't be predicted unless atmospheric pressure is unknown. It's not true. Okay, a compound resulting in a positive steric ammonium nitrate test would be most consistent with an IR spectrum containing which of the following absorbances? So what are we looking for? We just talked about it up here. What do we need? OH group, where would that be? B, 3350 to 2950. Which Newman projection depicts 1-bromo-2-methylpropane in its most stable conformation? A, eclipsed? No. B, would that be its most stable? No, because it is 1-bromo-2-methylpropane, but you've got both methyl groups interacting with the bromo group, which bromines are fairly large, so they'll have some interaction there. C, yes, that would be the best way to spread out those methyl groups. And D, why is D not true? It's just one bromopropane. We forgot the methyl group. So the answer is C. When bromoethylbenzene is heated in the presence of excess quinoline, styrene is produced. In this reaction, quinoline serves as, is it solvent? Yes. Is it the solvent and the non-nucleophilic base? Yes. So it is also, it's not the nucleophilic base and it's not a co-distillant, so the answer is B. 16. The following plot was obtained from experiment 4 for the separation of an alkene and an alkane. Which of the statements below is incorrect? Fractions B and D should be utilized for alkene testing. That one's true. Approximately 10 milliliters of products were obtained in the pure form. That's true. The tail on fraction D indicates additional low boiling impurities beginning to distill. No, that's just you running out of mixture, right, to distill. So the one that's incorrect is D, or sorry, C. For D, fraction A contains low boiling impurities. That's true as well. So the answer is C. Which of the following is the structure of the dimer of cyclopentadiene before it is cracked? So this one is just picking which one is right. The answer is C, okay? So you've got to go back and look at, if you can't see why it's C, go back and look at dicyclopentadiene and ways you could draw it, and it should look like C. student added 10 times more initiator than directed to his or her styrene for the radical polymerization of their styrene. Which of the following is most likely? A very high molecular weight polymer was obtained. No. A very low molecular weight polymer was obtained.
Yeah.
Yes. A high yield polymer was obtained. That's not going to happen. And the amount of initiator had no effect. That's not true either. So the answer is B. Okay, which of the following is true? N-phenolmalamide is an electron-rich diene. No. N-phenolmalamide is an electron-rich dienophile. Yes. N-phenolmalamide is an electron-poor diene. No. N-phenolmalamide is an electron-poor dienophile. So was it B or D? Is it electron-rich or electron-poor?
Electron-poor.
It's going to be electron-poor, so answer D. So you want dienophile is electron poor. Diene you want to be electron rich. In experiment 12, the dienophile was N-phenolmalamide, so it was an electron poor dienophile. Okay. The TLC plate shown below was run in 1:1 ethyl acetate hexane to increase the RF values and improve the resolution of the two spots. A new plate with the same reaction mixture should be developed in which of the following eluents? Just hexane? No. 1 to 3 ethyl acetate to hexane? Think about it. Okay. So you got 1 part hexane, 3 parts ethyl acetate. Sorry, 1 part ethyl acetate, 3 parts hexane. 3 to 1 ethyl acetate hexane. So you've got 3 parts ethyl acetate, 1 part hexane. So now you have more ethyl acetate. That'll make a more polar solvent. So the answer is C. You wouldn't. Water is more polar, but you're never going to develop a TLC plate in water because you'll dissolve your silica. You won't actually develop the TLC plate. So you need to think about what would be, you want an organic solvent. And you have to be careful of even alcohols. Alcohols will dissolve silica too, so you would never run a TLC plate usually in like 100% methanol. Okay? Okay. So we have a TLC plate shown below, used to monitor the progress of a reaction of A and B. It gives product C. Which of the following is not a correct conclusion for this TLC plate? Okay, so the product is more polar than both the starting materials. There's a little typo here. Than both of your starting materials. Yes, so our product is, we've got A and B. Our product then is going to be this spot here in the reaction mixture, right? The new spot. So that's more polar. B has been consumed in the reaction.
Yeah.
Yes, because we don't have any B left. The reaction will not proceed any further. Yes, because we've run out of B. Additional B should be added. Yes. The reaction mixture contains only pure product. No. So the answer is F. What is the RF of the spot on the TLC plate given below? Well, I mean, 0.25, is that reasonable? No. 0.35? 0.75? Yes. 0.95 would be too high, so the answer is C. In the workup of experiment 8, the Grignard synthesis of a secondary alcohol, Joe's student skipped the aqueous sodium bicarbonate wash of his ether solution containing his alcohol product, prior to adding magnesium sulfate, filtering, and distilling off the ether. Joe's professor warns him to look closely at his experiment 8 GC data. What should Joe be looking for? Alkenes. By not making sure the ethereal solution was neutral or basic, Joe may have allowed residual sulfuric acid and the heat of his distillation to catalyze an E1 reaction. What do you think? That actually is the answer, A, because that E1 reaction would then lead to formation of the alkenes. Alkenes, so why are the others not true? For B, alkenes, by not removing the last traces of water from his ether, Joe may have allowed residual water to catalyze an E2 reaction. Was that going to happen?
Did still
No.
water.
No. Ketone, by not making sure the ethereal solution was neutral basic, Joe may have allowed residual sulfuric acid, the heat, to catalyze reduction of his alcohol. Would that happen? You can form ketone, but is it from the sulfuric acid? No. It's from either adding your aldehyde too quickly or air oxidation. Ketone, by not removing the last traces of water from the ether, Joe may have allowed residual water to catalyze air oxidation of his alcohol. That's not going to cause any, the workup he performed isn't going to lead necessarily to ketones. Other isomers of his alcohol, by not removing water and acid, Joe may have allowed carbanion rearrangements. No. Okay, so the answer was A. Joe's lab mate, Sally Sleuther, got unexpected results from her GC for experiments 8 and 11. She had intended to couple 1-bromopropane with butyraldehyde, aka butanol, in experiment 8 and dehydrate the resulting alcohol in experiment 11, but did not observe the expected alcohol or alkenes. So just from that, from 1-bromopropane and butyraldehyde, what would the alcohol be? What did you do? 4 heptanol, right? From 1-bromopropane and butyraldehyde, you should have made 4 heptanol. Does everybody agree?
Yes.
Hopefully, yes. Okay. And so you would have made what alkenes? Goes either direction, so you make 3 heptenes, right? Because when you're in the middle like that, it's going to be 3 heptenes.
No 4 heptenes.
Either way you look at it, right? Okay. Sally had no alcohol left from experiment 8, but she was able to rerun her experiment 11 sampled by GCMS and identify the compounds in the sample as trans and cis 3-nonene, trans and cis 4-nonene, decane, and 4-nonenone. Which of the following did Sally ultimately conclude she had done? So, accidentally used valeraldehyde or pentanol. Would that have caused the problem? What product would you have gotten with valeraldehyde? Oxanol, right? So that's not going to cause the problem. Accidentally used hexanol instead of butyraldehyde. Well, what of these would you have gotten from the hexanol? Would you get the 3 and 4-nonene? Yes. Would you get the 4-nonenone? Would you get the decade? No. So it's not B. Accidentally use 1-bromopentane instead of 1-bromopropane. Yes, right? Because then you will get the decane from the 1-bromopentane reacting with itself if you add it too quickly. And then you would have gotten the right alkenes and the right ketones. So the answer is C. How much magnesium sulfate is required to dry an ether solution containing an unknown amount of water? Exactly 1 gram, until the magnesium sulfate is clumpy, until some free-floating powder remains after the clumpy initially forms. You must add until there's no liquid remaining. Magnesium sulfate does not remove water from ether. C. So you add it until there's some free-flowing powder remains after the initial clumps have formed, and you never weigh out how much magnesium sulfate you use. In gas chromatography, GC compounds typically elute in the following order, from lowest to highest boiling point. Yes. From highest to lowest boiling point? No. From highest molecular weight to lowest molecular weight? No. From highest polarity to lowest polarity? No. And from lowest density to highest density? No. So the answer is A. Which of the following changes to a gas chromatography method would cause compounds to elute faster, increasing the oven temperature. Yes. Increasing the flow rate of the carrier gas. Decreasing the column length. Yes, so D, all of the above. The ratio of trans cis isomer of alkene in the acid catalyzed dehydration of a secondary alcohol is determined by antiparaplanar geometry of the alcohol, the relative thermodynamic stability of trans and cis isomers in the alkene, the amount of carbocation rearrangement occurred in the reaction, the electron withdrawing groups of the dienophile, or the S-cis conformation of the diene. B, the relative thermodynamic stability of trans and cis isomers of alkene. The purpose of the tubing, inverted funnel, and water trap in experiment 14 is to keep oxygen out of the reaction, to allow pressure to build up in the reaction, to trap the HBr and HCl that's given off by the reaction. Yes. To allow you to slowly suck water into your reaction mixture? No. To cool the reaction vapors for reflux? No. So the answer is C. The student received his GPC data for experiment 7 product from his instructor. The volume values for MN and MW were handwritten on the data, but he was not given a PDI, polydispersity index. His data had MN is equal to 4560, MW is 7590. What is the PDI? So what was it? So which one? Well, PDI, how do you calculate it? MW over MN, right? So that would be 1.66 D. Which of the following is not a mechanistic step of the acid catalyzed dehydration of a secondary alcohol? Is A one of them? B? No, you've got too many steps going on at once. C? Yes. And D? Yes. So the answer is B. You're not going to go through all of these steps all at the same time. You're going to lose water first before you're then removing protons and forming the alkene. Okay? Okay, D here, I've got to kind of show you all the answers in order to show you the math. I'm a good chemist. A lab mate of Joe and Sally. It's quite a lab effect going on there. Use 5.4 grams of magnesium, 40 mils of bromopropane to form a Grignard reagent, and then slowly add 70 mils of 3.6 molar solution of valoraldehyde in ether. She ultimately obtained 21.5 grams of 4-octanol. She is a pretty good chemist. She made a lot of alcohol. So what was IMA's yield? So what do we have to first figure out? Theoretical yield. Before we figure out theoretical yield, what do we need to know? Limiting reagent. So we have to go through and find our limiting reagent. So magnesium, divide grams by molecular weight, 0.22 moles. Bromopropane, convert to from milliliters to grams, then to moles, 0.439 moles. Valoraldehyde, convert from milliliters to liters, and then use molarity, 0.252 moles. So the limiting reagent is our magnesium. Multiply that, 0.22 moles times the mass of our product, 130.23. Then we get 29 grams of 4-octanol. If we take 21.5 divided by 29, we get 74%, so the answer is D. All right. Our last question. Based on your results from experiment 14, which product would you expect to predominate under thermodynamic reactions from the reaction of 1-bromo 2-methylpropane, so isobutyl bromide, with toluene in the presence of aluminum chloride? Okay? So drawing this here to kind of help you out. So we've got 1-bromo 2-methylpropane. Okay? The initial proton cation we would form once we eliminate our bromine from our bromide with the aluminum chloride is this cation here. It would rearrange to this cation potentially, right? So we go from secondary to tertiary, okay? Sorry, actually, even primary here to tertiary. So, what is, with thermodynamic conditions, what is going to be desired? What carbocation are you going to want? Tertiary, okay? So that's going to form tert-butyl, right? This is the tert-butyl group. We also talked about thermodynamic conditions. What's our thermodynamic product? Meta. So the answer is E. Meta tert-butyl toluene. E. So your exam will be very similar to this kind of format. Make sure that you study the lab manual, study the pre-lab lecture notes, study your quizzes, okay? We're not going to ask you in experiment 3, how many milliliters exactly of NaOH did you add? We're not going to ask you things like that, but you need to understand what happened in the experiments, understand the theory behind the experiments, understand the theory behind what you used, okay?